we have a sphere. No, no. We have a sphere that is half filled with water, and our mission would be to pull up that water from a vertical pipe piece. And the radius is 2 meters, okay, and this is 2 meters. And this one here is, this one piece is 1 meter. And so if you draw a coordinate axis, this is 3, this is 2, this is -2. And what we require to do is find the work that has to be exerted by the water, or that the pump must exert on the water to move it. So what we're going to do to solve this problem is slice this up into infinitely many, like a lot of cylinders. And so after we bring all of these cylinders together, what we are going to be finding is how much we are going to require to move one cylinder up. So what that means is assume that this is called y0. This is going to be y1, and just move it up y2, y3, y4 until we reach many y's. And each very small subinterval here is very small, and what we are tasked with finding is moving from y1, and if we have a cylinder, yeah, let me use the white color here. So if I have a cylinder like that, and it's infinitely small, and its width is exactly at y1, and I need to move that plate of water up to y2. So I am going to move a distance of delta yn. And in this distance, I'm going to calculate how much work was calculated, and I'm going to do that for every single plate. So I'm going to go from here, from taking this plate, and then going up and calculating the work, and just doing it again and again till we can calculate how much work is going to be required. So we're going to say what is needed in a general picture is I equals 0 to n minus 1 of the work needed to pump the cylinder of water at yi to yi plus 1. If you can do that and continue doing it up to up to the finish point, where of course delta yn is a very small number, then you will have a very good approximation of the work it takes. So what is the work equal to? Force times distance. Well, we're going to have a problem. We're not given the mass of each slice. So how are we going to do that? Well, we're going to assume that mass equals density times volume. That is a physical law. We don't assume it. It is actual truth, okay? And so that's because density equals mass over volume. Mass equals density times volume. So I'm going to bring the force, which equals mass times acceleration. Acceleration is 9.8 meters a second squared. The mass is equal to density times volume. The mass of water is 1,000 kilograms per meter cubed. And the volume is going to be the volume of that very small movement of that sphere, or sorry, of that cylinder as it is going up So we're going to need to bring volume of that cylinder. And if it doesn't make sense now, I promise it will. Just a second. And so I'm going to put the volume here, and then I'm going to multiply by the distance. Now, what is the distance? It's going to be all the way up here. Okay? And so for this cylinder, it's going to go way up. For this, it's going to way less up, less up, less up. Okay, so let's try to figure out first what the volume is going to equal to. The volume is equal to, well, assume that this is not a cylinder, but it's just like, because it's very small, it's just like a circle. Okay, and so the circle has a radius of r. And doing pi r squared, you are going to get the area. And multiplying that by its height, you will get the volume of the cylinder. So I hope that makes sense. So what we're trying to do is we have a load. So that part about assuming that there is no height at all is false on my part. Sorry for it. So it is actually a cylinder. And I'm trying to bring the volume. So how am I going to do it? I'm going to bring the area of the base and multiply it by the height. So what's the area of the base? It's going to be pi r squared. Well, what is r squared? Well, r is equal to x, right? So yeah, we're going to need the equation. So we need the equation of the circle here in order to figure out what it is. So we know the equation of the circle is x squared plus y squared equals r squared. And knowing that the radius is equal to 2, we know that that is going to be 4. And we need x because x is equal to the radius. Think about it, like here to here, it's just the radius. So x is going to equal to 4 minus y squared, root 4 minus y squared. So putting that inside here, you're going to have 4 minus y squared rooted and then squared, then multiplied by pi. You have now the only the area of the cylinder. Now you need to bring the height. What is the height going to be? Well, the height is very simple, a variable called delta yn. It's a constant, sorry. And so delta yn, you bring it by bringing this point of integration, the points of integration here. So these are not the bounds. The bounds are going to be here, okay? It's going to be from this point to that point, okay? Sorry, I'm sorry. It's going to be from here to the surface level, okay? But we want to find what delta yn is going to be. So delta yn is the distance between each sphere, or each cylinder. So each cylinder has delta, no, not between each cylinder. It's the height of each cylinder. It's delta yn. And so delta yn is going to equal the point where I'm starting from, which is b minus a, divided by how many subintervals I need. So we're going to put that in delta yn, multiply that by distance, is this distance right over here. So what's the distance going to be? So we need to like follow a coordinate system. Okay, so the water is going to move. So we're going to use this coordinate axis, and this is going to be y plus going down. And so this is going to, no, this is not the best way to do it. I think y-axis should be going up. And we're going to be going to here is 0.3. Now the distance is not 3 all the time. The distance is 3, and it's going to be minus the point you're at, 3 minus yi. Because now you want to move this way if you're here. So that's going to be 3 minus yi. If you're at this distance, okay, it's going to be 3 minus the value. Okay, so you're going to say, wait a minute, why am I doing minus y? Shouldn't it be 3? Shouldn't it be 3 plus yi? No, yi is the value. So at here, if you're going at minus 1, 3 minus minus 1 is going to be 4. And here, if you're at 1, 3 minus 1 is going to be 2. So the distance is going to be 3 minus yi. You know, let me get rid of this mess. And I'm going to write this in a neater way. So what we want to do is we want to find the limit as n approaches infinity of the integral of, the Riemann sum of I equals 0 and minus 1. So this is a left Riemann hand sum, left hand, okay? And so we have 9.8 meters a second squared times 1,000 meters, 1,000 kilogram meter cubed times pi root 4 minus yi squared delta yn 3 minus yi. Let's put that into an integral from a to b. So in this case, we are going to go from 0 to 2.5. So, I just keep like not focusing because my attention's everywhere. So it's going to be minus 2 to 0. And we're going to go, so I'm going to do this one 9.8 times 1,000 times pi 4 minus yi. The delta y is going to be dy. This is going to be 3 minus yi. And that is our final answer. So I hope you learned something by it. And remember that our bounds of integration are only where the water is moving from. So since I had the circle, water was only moving from here to here, then my bounds will stay the same. Do not make the mistake of saying, oh, well, the water moved up here. No, you already counted for that upward movement in your equation.